All right, I'm Evan McLeod. This is part 3 of the Fundamentals of Aerodynamics Fluent project. So we're going to hop right in. Go over to Fluent. Gonna make this quick for you. I don't want to waste any time. We're going to start off with the geometry. So what we're doing here is we're making a semicircle and watching the way that the air flows around the semicircle. So we're going to be dealing with different types of flow that we'll get into later in the video. So we're going to start off, we're just going to work in the XY plane and create a circle. This is obviously going to be what our semicircle is. So according to the directions, we're going to want it to make a radius dimension of 10 meters. So let's go ahead and type that in. All right, 10 meters. So now what we want to do is draw a rectangle. Draw rectangle. All right, we want to make it a good enough size where it's not going to mess with our results, skew any data. I think that looks pretty good. As you can see, it actually locks into place and cuts that circle perfectly in half, so we don't have to mess around with the dimensions at all. Boom, we got a perfect semicircle. And it's about center. It might not be perfect, but that doesn't really matter. We have enough room on either side that it's not going to affect our results, so we can just go ahead and get straight to trimming. So let's go to Modify, Trim, get rid of the stuff we don't need, and there you go. So that's it. That's the shape that we're going to have. So now all that's left to do is go over to Concept, Surfaces from Sketches, and we're going to select the side, Apply, and Generate. There you go. So that's actually it for the geometry. Nice and simple. All right, now we're going to move on to the mesh. All right, so let's open it up. There it is, front and center. All right, so the first thing we're going to do is fix up the edge sizing. So we're going to start off by selecting the left, top, and the right edge. And we're going to select element size. We're going to change this to number of divisions. This is the best way that I've found to change the resolution of the mesh, so to speak. So we're going to set the number of divisions up to 200. For the purpose of this experiment, that's actually kind of overkill, especially considering we're not really interested in what's going on around these edges as much because all the experimentation is happening near the cylinder. But I figured I'd just make it really high anyways. So now we're selecting the bottom edge, including the semicircle. The reason we're selecting this separately is because we want finer mesh around this area because that's where all the data is happening. That's all the interesting stuff. So to get the most accurate data, we want to have basically the best resolution in that area, and that means having a finer mesh. So once again, we'll select number of divisions, and this time we're going to set it all the way up to 400. Now, it looks like there's more divisions around the semicircle than there is on the horizontal lines, but if we zoom in, you can see, boom, it's actually the same. It's even. It just looks like that because there's so many divisions, it created this visual glitch. But don't worry, everything's fine. It is the same number of divisions throughout the whole bottom edge there. All right, so now we're adding refinement. It's kind of unnecessary in this case because we're already going to have a really small mesh, or really fine mesh, I should say, but it's good practice to do a refinement anyways, so we're just going to do a refinement of 2, and that's going to be plenty. So once we've done that, we can click Generate. Through some editing, I'm going to speed this up, and boom, there's our mesh. So as you can see, it's super, super fine around the edges and even more fine around that bottom edge and that semicircle. As I zoom in, you can really see just how fine this mesh is. So we should be getting some really good, clear, accurate data, theoretically. All right, so the only thing left to do now with the mesh is to create some named selections. This is obviously very important. We're going to first off select the left edge, and we're going to name it Velocity Inlet. And then we're going to select the right edge. There we go. And we're going to name it Pressure Outlet. The reason we're doing this is it tells ANSYS that this left and right edge is exactly what we said, the pressure outlet and the velocity inlet. So the airflow is going to be going from left to right in our experiment. So now we're going to select the top edge. Now you might think I'm going to name this Wall, but I'm not. I'm actually going to name it Symmetry. I'm naming the top boundary Symmetry because we're simulating external flow in this part of the project. And so by saying symmetry, Fluent will automatically assign it a symmetry boundary condition, which applies a 0 normal velocity and a 0 shear stress. Right? So that's going to just kind of make sure this whole thing is external flow, and it's not going to mess up our data. As you can see, I just labeled the two bottom horizontal edges there walls, and then I am labeling the semicircular wall. I did name these separately as opposed to just making the whole bottom edge one wall, because we're interested in the data that's happening specifically around the semicircular wall. So if I were to name the whole bottom edge at once, our data would be concerned with the entire bottom edge, but we only want to know what's happening around the semicircle. So I named it a wall separately. Okay, so that's why I did that. So there's one thing left to do, and that's to select the whole face, and we're going to name it interior. There we go. All right, the reason for that is that also tells ANSYS we're interested in what's happening right here. Now, ANSYS almost certainly would have figured that out on its own, but if we didn't name it interior, we'd kind of be leaving ANSYS to guess what we're interested in this experiment. And so it's generally good practice to tell it, and we told it by labeling the whole thing interior. All right, so we can X out of that. Now we just need to right-click, and we're going to click Update. So that lightning bolt is going to change to a check mark when that's done. And there we go. And so that's it for the mesh. Now we can move on to the setup. All right, so let's open it up. We're going to do double precision as per usual. And boom. I always speed up the loading times. I don't have like the world's greatest computer. It just looks like it. All right, so yeah, looks like everything's good. You can see our mesh. It's very fine. So the inlets and outlets look good too. All right, so for this part, we're going to be doing viscous flow. I'm just going to stick with what's already there, but this is how we change it. That's the turbulence model I'm going with. And of course, I'm doing air. So the directions said to just do 1.2 for the density, and it didn't say anything about the viscosity in part 3, so just going to leave that as is. Okay. Okay, so we need to set the inlet velocity. Once again, part 3 directions say that we need to do a velocity of 25 meters per second. So just change that and apply. Okay. So this is where we can just double check that everything's labeled correctly. We got a pressure outlet for pressure outlet, the wall for that, symmetry is symmetry, velocity inlet is velocity inlet, walls is wall. So that's why earlier we named things the way they did, and I said it tells ANSYS what things are. This is how we double check that it got everything right, and it did. So now we're going over to residual. This is pretty much just going to mean it's going to take longer to converge and be more fine the smaller this number is. So we'll just add a couple zeros in there, get some more accurate data. If you make it super small, it's just going to take longer and longer to converge, but you'll get better data. But at a certain point, it's kind of diminishing return. So now we can initialize. Standard initialization, we're going to do from the velocity inlet. All right, so just double check the velocity. Looks like we're good to go. Okay, so now we can go over to run calculation. Whoops. Okay. And we're going to do 500. No, actually, let's do 1,000 iterations just to play safe. I mean, it's going to converge before then, but we'll just do 1,000. All right, calculate. And so there's our graph getting formed. Everything looks good. Sped that up, so it looked pretty cool. Okay. All right, and so we'll just see. All right, cool. So just want to double check. It says the solution has converged, so we're good to go. Took 169 iterations. Okay, so the first thing we want, I believe, is the contours. We want pressure and velocity contours. So yeah, we'll keep it static pressure, not pressure coefficient. Here I accidentally selected the semicircular wall. Okay, yeah, we just want it for the whole thing. So there you go. That's the pressure contour. It looks about right, as you can see at the stagnation point. It's the maximum pressure, and then where the velocity is fastest, kind of at the top of the cylinder, we have the least amount of pressure. So it makes sense. And then moving on to the velocity contour, this also makes sense. You can see it's the fastest at the top there, and then there's sort of nothing going on behind it because that's the wake region. So yeah, everything looks good. So next up we need our plots. We wanted pressure coefficient and velocity plots. So let's switch that to pressure coefficient as x-axis, which is having direction vector or position. So this is where we select semicircular wall. That's why we named it separately before. All right, and so that's what that looks like. And that's what it should look like. So we know we're good so far. Now we'll just switch this over to velocity. And there you go. This one's simple enough. It'll look different once we have inviscid flow. But for viscous, that's what that looks like. All right, and now we need the drag coefficient and the lift coefficient. So for drag coefficient, we're going to have x as 1 and y as 0. All right, that'll give us the drag force. Select semicircular wall, calculate, and there is the total. And then we're going to use the equation c equals f over 1/2 rho u squared a to get the drag coefficient. All right. So in that equation, F is the total force that we have right there, and C obviously is the coefficient. All right, so now we're going to change x to 0 and y to 1, and that's going to give us our total lift force. So let's print that. All right, so there's our total lift force, and we're just going to use that same equation to get the lift coefficient. Okay, and that's it for that. So that's everything we needed for viscous flow. Now we're just going to switch our model to inviscid. So now there's no turbulence. And we're going to do it all over again. All right, so first we need our contour diagrams. We don't need to change anything else in the setup. We do need to reinitialize, though. So once again, velocity inlet. We got inlet velocity of 25 meters per second. Same as before. All right, let's go ahead and run the calculation again. Just stick with 1,000 iterations. Okay. Speed this up. Boom. Alrighty. And then here we can see it did converge. Only, I believe this is 92 iterations. So this one was pretty quick. All right, so anyways, let's go to contours. Same as before. We're going to get our pressure contour first. And there we go. Perfectly symmetrical. Yeah, this makes sense. There's no turbulence in this model, so it's kind of like perfect, idealized inviscid flow. And so then our velocity is going to be the inverse of the pressure, and it is, which makes sense, right? Obviously, pressure and velocity are inversely related. So everything looks good there. Let's go ahead and go over to our x and y plots. So we'll start off with the pressure coefficient versus position plot. Oh, forgot to select semicircular wall. Okay, there we go. All right, so yeah, again, you can see this is the idealized version, or the inviscid version of the plot. So everything looks good there. Just kind of expand it for you. Get a good look. This is exactly what's going on in my report. I pretty much just screenshotted everything from this video to put in the report. So I'm showing you exactly how I got everything that's on the report. All right, so now we need the velocity plot. Okay, and there we go. Now it is no longer just a straight line. And I'll expand this just to get a good look at it. Alright, great. Only one thing left to do, and that is to get the drag force and the lift force. Okay, so let's run on over to forces. Let's get the drag force first. So x equals 1, y equals 0. And there it is. Pretty small this time. There it is. Forward point, blah, 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 blah. All right, and then let's do the lift force. And we'll see that the lift force is a lot higher than the drag force in this case. Much higher. 14,920. All right.
That's it.